I moved to Silicon Valley when I was 18 because I wanted to learn how to build computers. And I wish I could go back and ask my 18-year-old self some questions like, why do you want to build computers? I don't know how I got that in my head. But Silicon Valley complied and taught me how to build computers. And about 6 years after I'd finished my I'd moved to Silicon Valley, I finished my master's degree, and I was working in a Hewlett-Packard research lab, working on integrated circuit design, specifically integrated circuit testability. Now, test means something different in the hardware world than it does in the software world. In the software world, I still see a lot of people get up and talk about how important testing is and how critical it is to success. And one thing that you can get out of that is that you know that there are some people in the audience who haven't yet been convinced. And that doesn't happen in the hardware world. People in the hardware world know that they have to do a good job of testing because shipping bad parts is a kiss of death. It's very, very expensive to replace bad hardware once you've shipped it. So people put a lot of effort in on testing. So I worked on testability for a few years. And what I realized is that I actually liked the software portion of the hardware design process much more than I liked the hardware portion of the hardware design process. And so I started thinking more about software, and Hewlett-Packard was nice enough that they let me go to graduate school, and I kept trying to think, well, how could I take some of the stuff I like about hardware, which is all of the test and testability, and focus on getting it right, to the software world. I very quickly learned in the software world, we'll fix it later. If it's broken, we'll patch it. We can do that. Hardware, yeah, I understand you hardware guys, it's hard for you. For us software guys, it's not so bad. So just do the best you can, and then we'll make it right. I didn't like that. I looked for people who thought that maybe getting software right was important, and I found a little crowd of security people saying, hey, most of our security problems actually are software problems. And so I started digging into that, and I was pretty successful digging into that, and by that I mean I was able to finish a PhD. And that's some measure of success. And about 6 months after I did that, I got a call from a venture capitalist who said, have you ever thought about taking that and turning it into a company? I said, that'd be super cool, but I don't know how to do that. And he said, don't worry, I have people who do, and that's how I got into the security business, was taking my academic work and trying to prove it out. So I did that for about 7 years, and the company grew, and the company was successful, and it came time to decide whether or not we were going to go down the road that eventually led to an IPO, or whether or not we were going to sell it. We decided to sell it, and lo and behold, I was back working at Hewlett-Packard. So I thought what I'd try to do today is tell you a little bit about what I learned making that transition into software and then into security, and then coming back to where I am now, which is back working on software. I think, though, if we're going to talk about security very much, we have to start out talking about the NSA. That seems like maybe last year we could have talked about China or something, but now we have to talk about the NSA. So here's the deal with the NSA. If the NSA wants to know what's on your computer, they can know what's on your computer. Now they have a variety of tactics, though, that they will use to figure out what's on your computer. Their first choice is to corrupt someone upstream of you. So if they can tap the network because a network provider is working with them, or if you put your data onto Google and they can get Google to give it to them, then they'll do that. That's their first choice. Their second choice is to attack your software, to attack the software running on your machine, to break the software running on your computer. Their last choice, the choice of last resort, is actually what they got started doing, which is to break the cryptography on your computer. And in order to explain why, I thought I'd tell a little parable set in San Francisco. Now, at one point, the idea was that the streets were paved with gold in the United States, but of course we all know that's not true. But I will tell you this, everyone in San Francisco is an entrepreneur, including the people who are homeless, like Fred and Sam. Now, Fred and Sam decide to go into business. and they decide to go into the recycling business. And Joe is their first employee. And so they cart things back and forth between their two centers, Fred's cardboard box and Sam's tent, using a shopping cart. Yeah? All right, so is this system adequately secure? Yes? Raise your hand. Yes? Come on, this is fine. This is fine. They're storing soda cans and newspapers. This is perfectly reasonably secure for what they're doing with it. So business is good. So they decide to branch out into shipping gold bars. Yeah? Clearly there are some security risks here. So what do you do if you want to ship gold bars around? Well, you get an armored car, clearly for Joe, to drive the gold back and forth. Now, is this system reasonably secure? Thank you, you all got it right that time. That's good. No, this is really, really bad. The armored car is fine, but the endpoints didn't change. And the endpoints are the software on your computer. We have some reasonably good protocols for moving things around in a secure fashion, but the software that we put on the endpoints tends to be really, really bad. So one lesson you could take from that is that a security feature, like maybe you're using SSL to move data back and forth, is not a replacement for secure features. So when you do authentication, you do access control, maybe you do a really nice audit log, that's all good stuff, and you need to do that, just like an armored car would be part of a secure system for moving gold around. But it's insufficient. Maybe, is it too early for me to digress? I'll give you guys a little digression on this. I hope you enjoy making fun of mathematicians. Because I do, and the mathematicians are the ones who become the cryptographers. So a few years ago, maybe 3 or 4 years ago, NIST had a competition to choose the next secure hash function. And one of the entries was called MD6. Well, I didn't feel like I was really in a position to contribute to the mathematical portion of this because it turns out it's complicated. But I wanted to make fun of them anyway. So what we did is gathered up all of the code submissions for them and showed that the code submissions for almost every single hash function had vulnerabilities in it. And I had a great time. I thought it was great because I got to say, haha, the mathematicians can't code. Isn't that funny? And it turns out it got kind of odd. So at that time, the worm that was making its way around the internet was called Conficker. And it turns out that the worm writers were amateur cryptographers, or maybe cryptographic enthusiasts might be the right way to say it, because they had taken some of these unproven, really hash functions with no known properties and embedded them into their worm. And about 2 weeks after we announced that we'd found all of these vulnerabilities in all of these demonstration algorithms, they patched Conficker. It turns out that not only are they amateur cryptographers, but the worm writers care a lot about security. Oh, no, too fast. Let's talk about the NSA again. Here's my favorite story, or the favorite thing that I learned out of the whole NSA revelations of the last few months. You know, it's not all of the stuff that they're doing. The first time I went and talked to the NSA was probably maybe it was 1996 or so, when I first showed up at the NSA, and I was talking to them about hardware at the time, and I would ask them basic questions. Do you know what a stuck-at fault is, which is a very basic thing in hardware testing? And they would all just sort of look at each other, like they weren't sure what they were supposed to say. And there was a red light flashing the entire time I was in the room in order to make it clear there was somebody who was uncleared in their presence. Over the next decade, they got much more straightforward. And they would say, hey, you know, we're looking for vulnerabilities in code. And we do that to protect people, because then we take those vulnerabilities back to Microsoft or back to Google, and we tell them to patch their systems, unless the vulnerabilities are really good, and then we keep them. And they were very, very straightforward about it. Let's talk about how we got here, though. We've got about 50 or 60 years of computing experience, and we've been dealing with computer security through most of that. But really, computer security has its roots in communications security, which has a much, much longer history. So we could go all the way back to Caesar and talk about a Caesar cipher. You know Caesar cipher? It's a substitution cipher. You take maybe an A and replace it with a Q and et cetera. So now that's a grade school kind of a cipher to write. Was a Caesar cipher good security for Caesar? I have any takers on that? I have a lot of takers on that. Okay, I'd call that 50%. Well, good job, 50%. Caesar cipher was a very good cipher for Caesar because most of Caesar's enemies were illiterate. So as soon as you jumble things up at all, they're gone. So communication security stayed in approximately that state all the way through Abraham Lincoln's time, where we were sending encrypted messages over telegram wires. And it really started making leaps forward with the advent of the radio. Now, why was the radio such a big deal for secure communications? It's because it was the first time you could take your fleet, send them over the horizon, and give them new instructions. So now you could have your military power on the other side of the world and tell them what to do. You needed to be really careful, though, that nobody else was telling them what to do, yeah? So by the time we get to World War II, cryptography has really come into its own as a discipline, and is in fact incredibly important in the war effort, particularly in the Pacific. Now, maybe we got computing out of that cryptography effort, or major advances in computing in the European War, but it was the Pacific War where they won lots of battles because of cryptography. And then the next major leap takes place in the 70s, and that's Adlai, Revest, and Shamir up there in that picture in the top right. So that's R in the middle, S on the end, and A at the far side, that RSA algorithm. The RSA algorithm changes things in a big, big way. That's public key cryptography. Here's why things change then, because all of a sudden, people who've had no relationship before can enter into a trusted relationship. You don't really need that if you're a military, because you don't go making friends with other militaries all that easily. But if you're in business, you make new friends all the time. So public key cryptography was a big, big deal. And of course, once we had Netscape, then we had public key cryptography built into a technology that everybody can use. A few thousand years of communication security, I kind of boil it down to about one lesson. And here goes for communication security. Security is hard to measure. It's really, really difficult to know how much you have. There are a few reasons for that. One, you don't know what your adversary knows. They might know very little, they might be illiterate, or they might have just stolen all of your codes. You can't tell. Secondly, things change. So maybe you correctly measured the amount of security you have today, and then things shift just a little bit. One extra submarine gets caught, or one courier decides to go over to the other side, or maybe one system administrator decides to give away all your documents. And all of a sudden, your security posture changes substantially. Lastly, small mistakes have big, big consequences when it comes to communication security. So you think you've measured correctly, you miss a detail, and your whole analysis is wrong. So what are the consequences of security being hard to measure for communications? I'll give you 4 of them. The first one is you've got to be conservative. When you take a measurement, you really have to make sure that you're taking the worst case scenario, and the worst case scenario turns out to probably be about the expected case, because the worst case may actually be worse than you know. Second of all, keep it simple. I used to have to explain really carefully that simple is not the same thing as short, but Perl is sort of on its way out, and so I think maybe that's not as important a lesson these days. I don't know, but simple, and simple is not short. There are no absolutes. Any security person who comes and tells you, this is it, this is the thing that makes us secure, that doesn't pass the sniff test. Security is about assurance, it's not about proof. Lastly, security through obscurity doesn't work. You should assume that your adversaries know everything that you know. That's enough on communications security. Let's talk about computer security. Like communication security, computer security started out being mostly about government and military needs. And if you go back and you read their literature from the 60s or the 70s, it's mostly about things like access control, who gets to know what, when. There's one sort of glimmer of hope that comes in the 80s, actually out of the NSA. Nobody knew it was the NSA at the time it was published, but it was the Orange Book. And it explained, here's what you can look for when you evaluate a trusted system. And they explained the implementation of that system is actually critical to making a high security system. Now, when this photo was taken, I have to think that probably computer security mostly meant keeping the door to the computer room locked, right? And actually, it hasn't evolved a whole heck of a lot since then when you think about fundamental strategies. So there are 2 fundamental ways to defend a computer and 2 fundamental ways to attack a computer. When it comes to defense, there's isolation. In other words, don't let your computer talk to anything else. And if you think about why we have such a thing as a process, that's really about isolating this code from all the other code in the system. A virtual machine, a sandbox, a firewall, all sort of take this same position, which is the default answer is no. So isolation. Secondly, when isolation doesn't work, we monitor. So you can monitor by handing people by using privileges, handing them a receipt that gets them through the door. Or you can use what's called complete mediation, where you sit between whatever is making the request and whatever is being requested. So if you think about a virtual machine, there's a hypervisor there that watches every time something in the virtual machine wants to talk to the hardware, and that's complete mediation. That's defense. That's it. All computer security defense comes down to doing those 2 things. Attack, there are 2 strategies. First, brute force. Just try everything. Second, violate some assumptions. You could find a loophole somewhere. Or you can step outside of the system. So for example, when you come up with a very good password system, and then someone tapes the password to the bottom of the keyboard, then you can step outside of that system by turning the keyboard over. And really, attacking computers comes down to those 2 things. Just try it all, suck up all the data, maybe, or violate somebody's assumptions. Why do people get so surprised about computer security problems? I mean, forgive me. I don't want to sound jaded. I don't mean that we are destined to have all these problems. I want to introduce the idea that there's actually a very good reason why people's intuition doesn't match what they get out of computer security often. Really, computer security breaks people's intrinsic security model in two really big ways. One, it doesn't match physical security very well. So physical security is very linear. For example, if you would like to rob a bank, you will need to get a vehicle that can take all the loot away. And the amount that you can take from the bank is limited by the amount you can transport. Secondly, in the physical world, we primarily rely on accountability, an accountability model, in order to keep our world secure. It's really not that hard to break into my house, for example, because I have windows. And if you wanted to throw a brick through the window and come into my house, you could. Why? Why wouldn't people do that? Because they will be held accountable for their actions, or the likelihood of them being held accountable for their actions is enough to deter them. Computer security doesn't work this way. First of all, it's very, very nonlinear. How many bitcoins can I fit into my car? All of them, right? Secondly, there's very, very little accountability. And because of that lack of accountability for computer systems today, then we have to rely on prevention to a much, much greater degree than we're used to in our physical world. So that's why people get surprised by computer security. You know, it's hard to talk. Computer security has become a really big thing. There's a lot, because there's a lot of flavors of computer security. Try this. This is only a thought experiment. Kill somebody. You will find out just exactly what your digital fingerprint looks like if you kill somebody. Because the very first thing the police are going to do is they're going to figure out where were your digital devices, who were you talking to, and what does your digital world say about you. And the police may or may not beat the newspaper to that these days. So that's all about forensics. Data security is all about digital rights management and keeping databases secure and making sure people don't get more than their fair share of a database. There's security information management, which is what your IT department does when they provision you an account. Then there's, they also patch machines. That's pretty important. There's Band-Aid security. This is my least favorite kind of security. Host-based security, such as antivirus, is a Band-Aid. The reason why we have antivirus is because the systems we have leave opportunities for viruses. Same with network security. The reason we have firewalls. Actually, this is the way that I explained security, software security, which I'll get to in a moment, to investors. What is a firewall made out of? I mean, what is it? Well, it's a computer. It's got some software on it, but that software is very specialized, and it's supposed to be able to take a lot of abuse. Well, why is that a specialized thing to have it take a lot of abuse? That's an oddity, and it's something that's not quite right in the world. And actually, software security, my favorite kind of computer security, and the reason I'm talking to you about security, is about how do you write code that isn't vulnerable. Knuth is awesome. Programming is hard. That's why we end up having to talk about it so much, right? Because it's hard. I tell programmers, hey, it's you that's going to decide whether or not this system is secure or not. Mostly programmers don't like to hear that. Historically speaking, they haven't been told that. They say, hey, that wasn't my job yesterday. Why are you, hey, look, I've already got this hard thing to do. Knuth says it's hard, and now you're telling me I have to do more? And so they start trying to dodge it. Here's maybe the very first dodge. The first dodge is, well, hey, security is really part of quality. If I have good quality control over my system, then I'll have good security control over it too. So Kernighan, as part of trying to explain why C wasn't a disaster, tried saying, well, hey, look, guys, it's your fault if your program doesn't work right. You're not practicing what you would call defensive programming. So here's a quality technique from Kernighan. Here's a C function that takes a file and a message, and it crashes if you pass it a null file or a null message. So you might say, well, I'm going to add some error handling to that. I will log an error if file is null. I'll log an error if message is null. And only then will I call this wonderful printf routine that you've given me. Turns out that doesn't work either. This code here is just as vulnerable as the first piece of code to what's called a format string attack, where you can actually overwrite the stack and take over the process using input that looks funny, like that stuff along the bottom. Here's what you have to do if you want to make this secure. You have to supply the format string. It's a little difference. Given the input that you have for your program, it may never be relevant to the proper functioning of your program, only to the secure functioning of your program. You could look at it kind of like this, because quality and security do actually have a close relationship. With quality, you can't bolt it on at the end. You can't expect the QA department will deliver quality. Security is the same thing. You can't bolt it on at the end, so you have to build it in. With quality, we're asking, is the program going to do what it's supposed to do? Are the users going to like it? So with security, though, the question is, does the program do some extra stuff? Maybe it makes users very happy. Maybe it makes attackers very happy, too. So we have to shift from the user mindset to the attacker mindset. So really, it's not about what will the mainstream do with your software. It's about what are the corner cases. What are the things that you can push this program to do in the extreme? We're also not worried about what we stand to gain, typically, when we look at security. We're worried about what do we stand to lose. Here's another take at the programmer's dodge. So they say, okay, fine, the security stuff sounds complicated. You've convinced me of that. It sounds hard. Okay, so then we need an expert. And the expert can come in and they can do a penetration test, and they can tell me all of the places where my software is bad. Then the penetration test comes back, and it's got a very, very long list of results. Okay, that's too much. That's too much. I'm not going to fix a problem with the code that's theoretical. I'm only going to fix the problem if you can prove to me that a bad guy can do something bad. Or you might say, some penetration testing results are clearly dangerous. Fine, you got me, I'm going to fix the code. Other code I can look at and I can say it's safe. The biggest problem we run into is in the middle. It's where you say, show me why that's a bad thing. Okay, so now if we go back to a communications security history, you can kind of understand why this is such a trap. It's because it requires you to be as good an attacker as your attacker will be. Are you trying to play defense or are you trying to play offense? Because if you require playing good offense before you play defense, you will lose. Let me illustrate that. Have you heard of Citibank? They're too big to fail? Does that ring a bell? So they have money. And they built an iPhone app. And you could go, look at your money in the iPhone app. And the security testers came back and they said, wait a minute. You just put a bunch of information about my money on that phone. The programmers came back and they said, no. That's an iPhone. It's a closed system. It's a walled garden. If you can actually crack in there and get that iPhone, well, you can do anything you want. You've become that person. We don't need to protect this any more than this. There's no way for a bad guy to make use of the fact that there's bank account information on that device. because they didn't think about what else that device did. And of course, when the iPhone first came out, you backed up your device onto your computer, which meant all of your bank account information went onto the computer. And bad guys are really good at getting on Windows machines. So that's an example, just sort of one case about where the exploitability trap will burn you. I'll try to generalize that to a certain extent and talk about Bertrand Russell's chicken. Are you familiar with Bertrand Russell? Is it the Principia Mathematica? He's sort of the grandfather or great-grandfather of computing. So you had Bertrand Russell, led to Gödel, led to Turing. Is sort of where we are in history. But he likes to talk about this chicken. And the chicken has a worldview. And the chicken's worldview is created by its history, by what it has experienced. So it experiences a barnyard that has food, that has shelter, that has companions. And when you ask the chicken to describe the future, the chicken will describe a future full of food and shelter and companions because that's what it knows until one day. And that's the same problem that we face with computer security, where as a programmer, your intuition about the way the world works and who wants to attack your software and what's good code and what's bad code can change very quickly. But when it does change, it's probably too late. Is all of this very negative? I'm going to try and pull out. I love Henry Petrosky, and this is a tremendous book. It's old right now, but that doesn't hurt it, because it's not about computers, and it's not about security. It's about building stuff, like space shuttles and bridges. And here's what Petrosky says. He says, success is foreseeing failure. Or, put another way, if you want to succeed, you have to know how you're likely to fail. Okay, I like that a lot, because now we can leverage our 50 or 60 years of computer security and how software systems fail and start talking about how to make strong systems. My first bit of advice on building software that's strong is educate developers. Hey, if you work for a big company, do you have to take some security training? Who has to take security training as part of their job? Yeah. Just leave your hand up. Leave your hand up. Whose security training sucks? Yeah, that's what I thought. Yeah. It's really pretty awful. Generic security training is pretty much useless. If this link makes you feel funny, don't click it. I don't see a tremendous amount of value in that. Security training for developers, though, looking at what vulnerable code looks like and what safe code looks like, I think actually is valuable. And the second thing that I'll put on that list is code review. Code review specifically augmented with a static analysis tool. And I'll talk about static analysis here just a little bit. This is what I did my PhD on and what I started a company on. I ended up feeling like I didn't publish enough as a PhD student, so I ended up writing a book about it too. I believe in static analysis, even though I'm not in this business anymore. Static analysis is good because it allows you to examine all paths through a particular piece of code. And static analysis is good because you can bring some security knowledge with you as you look at a piece of code. I'll show you what I mean by that. So here's a little piece of vulnerable code. If you have a good static analysis tool, it will say, oh, you're getting input from a network and you're putting in a buffer. All right. Now you take that buffer, you copy it over into a new buffer, and then you call exec on that buffer. Well, I'm going to call that a command injection vulnerability. So that little bit of data flow analysis that we're doing there is not too hard on 3 lines of code. It's much more complicated in an interprocedural program with millions of lines in it. But you can do a lot better at finding vulnerabilities with static analysis than you can without static analysis. I'll make one more note on static analysis as a tool. If I could nominate a banner carrier for all tools, it would be the chainsaw. And I think that the chainsaw is an excellent representative tool for two reasons. First of all, if you've got a chainsaw, you respect the chainsaw, yeah? Yeah, right? I see a lot of software tools that don't get nearly as much respect as a chainsaw gets. People aren't nearly so concerned about getting the right result and not getting the wrong result, yeah? Secondly, people understand that a chainsaw is a tool. In other words, you don't put it down and it does the work for you. You wield the tool, and it helps you accomplish the job. And I would say the same thing about static analysis tools as part of doing code review. They're great as a tool, but they do not make the code more secure for you. I'll make one more note on what can you do to make your software development organization more secure. And actually, I posed that. I inflected it a little differently. I said, what do you do to make your organization more secure? And I posed that question to companies on this list and actually quite a few more. And I was amazed when they answered me. They actually sat down and talked about it with me. And what we found was actually there's quite a bit of similarity between the security practices in a lot of large software generating organizations. I put up Wells Fargo. I could have put up a long list of other banks too, Goldman Sachs, for example. And you know, those big banks generate a lot of software, as much software as the big software makers do, actually. And they all do very similar things. Now, the banks tend to be more concerned about making the regulator happy. And the software developers are more concerned about what happens when their software goes out into the world. Because, for instance, Google ships a lot more software into devices via Android than a big bank does. So their concerns are not the same, but they are similar. Similar enough that we put together this building security and maturity model at BSIMM.com, and you can look at, in aggregate, what do all of these companies do to be more mature about building security into their software. I have parting thoughts that I'll probably go through until they turn off my microphone. I hope you've enjoyed hearing a little bit of history, a little bit of context around building software. But if you're really more, I want to go write another line of code, if that's where you are mentally, let me tell you what to do with the next line of code that you write. Be stingy about accepting input. Be very, very mindful about taking input that meets your requirements and does nothing else. If you do that well, you will eliminate maybe half of the software security problems in your code. Second piece of advice, get help with security features. When you go to Stack Overflow and read about how to hash passwords, you do not become a password hashing expert. In fact, you make yourself a sitting duck. So when you need to build robust security features, get some help from an outside expert, the same way you'd go get domain expertise when you're building software or about any other deep subject. Next on my list, minimize decisions. I think that's probably good advice for doing any kind of software development, but it really, really matters when it comes to security. Now, there are two audiences to minimize decisions for. One is your users. This SSL certificate looks bogus, okay? Is not helpful. So don't force your user into making security decisions where they are not going to be able to find their way through. Second of all, minimize security decisions for your developers. Once you've written the API for accepting only the input you need, don't leave a developer wondering about what they're supposed to call. Make the secure way the simple way and the default way. Okay, just one more. Here's the problem. Fundamentally, the problem, I think, with getting security right as a software developer. The problem is that the feedback cycles are very, very long. You make a security mistake, your code might be attacked, it might not be attacked. Or it might be attacked 10 years from now. That means that it's hard to learn. So if you really want to do a good job of building secure software, you need to find a way that you build feedback cycles into your system. In other words, now I can explain, I guess I can explain the title of my talk. 50 minutes later, I can explain what this means. Getting there and back again, over and over again, is what will make you good at anything. And it's particularly important when it comes to building secure code. Thank you.
So the question goes like this. How would you evaluate static analysis tools? Choosing a bad one would just give you a false sense of security, wouldn't it?
Evaluating static analysis tools is actually very similar to building static analysis tools. I mean, maybe the first thing you've got to decide before you build something is that you're not satisfied with anything that's available to you, right? And how do you decide in this particular case when you're not satisfied that something's available to you? Well, you need to look at examples. You need to. So here's how I evaluate static analysis tools. I get some bad code. And I get the good code that does the same thing, side by side. And I get multiple examples of that. And then I say, well, can I find the bad code? And can I distinguish the bad code from the good code with this static analysis tool? If I can do that a lot of the time, I've got a good one.
But that kind of assumes that you already know bad code from good code.
Yes. You have to know what you're looking for. If you don't know what you're looking for, then you're basically just going to buy a car the way my wife buys a car. It's got the right color.
Thanks, and thank you for an excellent talk. I enjoyed it very much. So how do you, if you have a static analysis tool that tells the users or the programmers that, oh, this software is not secure, how do you make it really explain it to the users why it's not secure? I mean, maybe the software was fine, and then I go and make a modification in one part of the system, and then security breaks down in some other part of the system. Does that make sense?
I'm sorry, I'm not positive I understand. So,
okay.
So you got this magic static analysis box, and out of it pops a list of things that are wrong with your code.
Yes, and the programmer needs to understand why. What do I do to fix this?
A list of things that are wrong with your code doesn't actually make you any more secure. What makes you more secure is when somebody takes something off the list and changes it and makes it better, right?
Right.
And so the question is, how do you go from here's a bad thing to something that's better, right?
Yes.
And actually, that's why I put one thing in front of static analysis, and that is developer education. Developers need to be able to look at that and say, oh, I saw that. I understand why this thing is bad, and I know the kind of thing that you do to correct it. What the static analysis is good for is finding all of those corner cases, right? So it's good for bringing some security knowledge with it. For instance, where can input arrive in your program? It turns out, for instance, DNS can get information into your program in some ways that you might not expect. So static analysis is good for bringing that knowledge with it. But once you've got a result, then the programmer has to be able to act on it. And a programmer who has never thought about security before isn't going to be able to do much with that. So number one, education. Number two, code review. Thank you.